Thank you very much, Emmanuel. Good afternoon, ladies and gentlemen. Thank you for the very kind invitation, which I accepted with pleasure to be here. I always enjoy France and especially Lyon. I will try in the next 45 minutes or so to cover what I do in one semester in our university. So I'll try to give you an overview on seismic retrofitting of concrete and masonry structures with composites. Speaking of my university, this is where I come from Patras, from the Department of Civil Engineering, where we are lucky enough to have very good testing facilities to do nearly full-scale testing, pseudodynamic testing of structures. There's also a relatively small shaking table, the materials lab, and our latest lab is one on fire testing, which we would like to explore as much as possible in the years to come. These are the contents of my presentation. After a very short introduction, I will talk about the seismic retrofitting of reinforced concrete with FRPs. That will cover flexural, SHEAR, as well as through confinement strengthening. And then I will spend some time to talk about masonry, retrofitted with FRPs, masonry subjected to in-plane or out-of-plane actions. Confinement also will be discussed. And at the end, I will spend some time talking about strengthening and retrofitting with cement-based, with inorganic materials, with fibers or steel or other types of fibers combined with inorganic materials, as was discussed earlier today as well. I guess everybody knows that FRPs are basically made by combining fibers, carbon, glass, aramide, basalt, with epoxies. They are also available as prefabricated elements. So practically we have two different products. We have flexible fabrics and fibers and relatively stiff products which are epoxy bonded on substrates. This is the material we have to deal with. If there is one thing that an engineer should know about these materials is that fibers behave linear elastic all the way to failure, unlike steel, mild steel. And depending on the type of fiber, we can have an elastic modulus from 70 to 230, even more, even up to 600 gigapascals. And of course, loads are only carried by the fiber. So our material is not isotropic as in the case of steel. Here I have tried to summarize the advantages and disadvantages of the FRP, of the so-called FRP strengthening technique. Our materials are lightweight. They are resistant to corrosion. They are available in very long lengths. It is easy to apply them without much obstruction of occupancy. They have high strength, high tensile strength. It's very important that they do not modify, we do not change the geometry of cross-sections when we use FRPs to do retrofitting. And we do not also modify the stiffness characteristics. That may be thought as a disadvantage, as a negative point, as well as a positive one, if the objective of the intervention is to make a structure stiffer. So using FRPs to make structures stiff is not the way to go. That is something that we should remember. On the negative side, we have a higher materials cost. We have lack of ductility. There is no yielding of the material per se. However, there is a very high deformation capacity, so we get a lot of ductility from structural members retrofitted by composites. There is, of course, a need for fire protection, and they need to learn more about these materials. Before playing with FRPs, we were used to a number of different techniques, mainly related to the application of steel To name a few, I will refer to jacketing, to shotcrete, to jacketing by using shotcrete, or to the application of steel plates, steel jacketing, the addition of shear walls, you name it. And then we have the two basic FRP techniques. We do wrapping of structural members with flexible products, or we epoxy bond relatively rigid elements like carbon-based laminates, for example, externally. Let me start with flexural strengthening. The idea is to add capacity, to add flexural capacity to a flexural member, a beam, a bridge, a slab, whatever. This is what we start with. The red line is a typical, simplified, of course, response of a flexural member. And with the green lines, you see how that response is modified by adding extra flexural reinforcement using FRPs. The point to remember here is that we don't really change the stiffness. There is a very slight increase in stiffness. Of course, there is a lot of strength gained by the method, but there is also a reduction in ductility. This is not due to the fact that we add FRPs. This is due to the fact that we increase the amount of tension reinforcement. And it has nothing to do with the material itself. And most likely, failure is brittle, is catastrophic due to the sudden debonding of the member, unless we do something to prevent it, unless we use anchorages, for instance. This is definitely not the way to do flexural strengthening of columns. Although it has been done in many projects, this is not the way to do it. Beams are very easy. Columns are a bit trickier. By adding external reinforcement in columns, top to bottom, we only spend money. We really have to pass the reinforcement through the joints. We have to anchor them through the joints and also do something at the ends to prevent local buckling, etc. So if the objective is to do flexural strengthening of columns, we need to remember that we must extend the material through the joints, slabs, foundations, whatever. Because typically this is where moments are high. There are a number of ways to do it. One is to use near surface mounted reinforcement, that is FRP or even steel rebars placed inside grooves. Or we can use fabrics with the fibers in the longitudinal direction of columns, anchored using spike anchors. That was discussed by other presenters earlier. Fixed in the foundation blocks, in the slabs, or in the joints. Here, the point to remember is that by applying this method, we only increase the flexural resistance. If we take a look at axial force versus bending moment diagrams, interaction diagrams for these members, there is no gain, there is practically no gain in axial resistance. We only increase the flexural capacity. So the method is beneficial only if the axial load is relatively low, let's say below 0.3, 0.4 of the strength, 30, 40% of the axial capacity. And that's a typical comparison of a reinforced concrete column, flexurally strengthened with FRPs. That's a control specimen that is prior to adding the flexural reinforcement, and this is what we get by an identical specimen with this extra externally applied reinforcement. There is an increase in the strength, but practically no increase at all in the stiffness. When it comes to shear strengthening, the objective of the intervention here is to modify the failure mode from brittle, with very low ductility, to very nice ductile flexural type with stable hysteresis loops. So we practically have to add extra shear resistance to members, and the question is, how do I calculate, how do I design, how do I dimension the externally applied reinforcement to get this extra resistance? The philosophy here is identical to stirrups in reinforced concrete. We have to think of the fibers as an infinite number of stirrups. An infinite. We have thousands, millions of tiny stirrups applied externally. So they have to be applied in the direction of the principal tensile stresses, basically. These are typical configurations of FRPs to do shear strengthening. In the case of T-beams, we have many options. We can use, normally we do this one. We use three-sided jacketing with or without anchors. This is a two-sided jacketing, which I would avoid. We have no reason to do that. It's not effective at all. It will debond prematurely. We can simply continue the jacket all around in the web. Another possibility is to anchor the fibers through the slabs, as was shown also earlier in several presentations. Of course, one expects that this is much more effective than what we have here, because those tension elements, those stirrup type elements are fully anchored. They form a loop, so they carry stresses, and most likely the failure mechanism here will be tensile fracture of the fibers as opposed to debonding, which might be the case if we have open jackets. When it comes to columns, our life is of course much easier. Typically it is quite easy. We have access around columns. Even if we don't, all we have to do is to remove some of the parts of the infill walls adjacent to the columns to get access. So normally, making those closed jackets in the case of columns is easy. A few photos to illustrate the concept. You see wrapping of columns to increase the shear capacity with carbon or with glass fibers. Wrapping of members supporting large structures for shear strengthening, as well as for confinement, which I will discuss a bit later. We can do many very good jobs. You see stirrup type elements, straight fibers, or wrapping of columns to increase the shear resistance. We can also do a lousy job if we do the application the way you see here. It is not a good solution to try to apply the reinforcement, to follow the profile of the cross-section, unless we do something about the anchorage that will debond prematurely and will not really add any capacity to the member. When it comes to calculations, to the dimensioning of shear strengthening, we have one unknown, that is how much extra capacity, how much additional shear strength I need to add to my structural member. And that unknown is, this is the, yeah, it's right here. We have one unknown. This is the total capacity, and all we have to do is to relate the contribution of the FRP to the shear capacity of the structural member to the properties of the jacket. One possibility is to use formulas, equations which are identical to what we have for the case of steel stirrups, internal stirrups, the only difference being the fact that we don't have a yield stress for our strengthening element. We have an effective stress. We have the stress in the FRP at failure of the jacket, which depends very much on the failure mode. It depends on whether the fibers will rupture or will debond, and that is something that we have to take into account. Speaking about debonding, you see what I mean here. This is an open jacket. These are strips applied to do shear strengthening. The fibers are not continuous, so most likely what we expect is this type of debonding in the free part, which is also shown here. So the fibers are not utilized to their full capacity, and that is something to be taken into account in design. One way to exhaust the capacity of the fibers is to combine the system, those open jackets, with anchors, with spike anchors, that is to anchor the fiber, to transfer stresses from the jacket through the slabs in the case of T-beams. Here is one way to prove that these anchors are extremely effective. You may see the extra shear capacity provided by an open jacket to a typical T-beam, we have something in the order of, let's say, 39–40% if we do nothing about anchors. And then depending on the configuration of the anchors, we can increase that capacity to up from 39 to 50 to more than 100%. Apparently the best system is somewhere here where those anchors are placed nearly vertical and not horizontally in the web, but as much as vertical as practically possible through the slab. So if I compare that column here to the very first one, I have a tremendous increase in the effectiveness of the system if I combine those U-shaped jackets with anchors. Shear strengthening of joints, that was very nicely covered by Maurizio this morning. That's a very tricky area here. We typically get shear failures in joints due to the lack of continuous stirrup type reinforcement in those elements. And one way of shear strengthening the joints is through the application of FRPs. Ideally, we should place the material, the fibers in two directions here, both horizontally as well as vertically. If we choose one of the two methods, the horizontal configuration is preferable, but ideally we should do both. And it's really important to emphasize here that by simply placing fibers in the panel, in the joint panel, is not enough. We really have to extend the fibers outside the joint to properly anchor those fabrics so that the fibers in the joint region will be activated before debonding takes place. That's a typical response of a joint without any retrofitting, without any jacketing, with FRPs, and you see how that may increase, how the shear capacity of the joint may increase with one or with two layers of a low-cost, low-thickness CFRP fabric. We get increases in strength in the order of 40 to 60, 70% easily with a couple of layers. A few applications on shear strengthening of joints. So you see the fabrics applied horizontally in this case. Time to say a few things about confinement, which is probably the most important application of FRPs in seismic retrofitting. We do confinement for many reasons. They were discussed by Maurizio. I have tried to summarize them here as well. If we do full wrapping of columns, we normally do this to increase the axial capacity of members. But if our interest is increasing the deformation capacity, we only need to do local jacketing, only at the ends of members to confine those areas. We do this local jacketing also to prevent failures at lap splices and also to delay or to even to eliminate local buckling of the longitudinal reinforcement if our stirrups are at a relatively large spacing. So those are the basic reasons why confinement is done by FRPs. And why FRPs as confining elements? They are very easy to apply. This is the proof, that's a huge column and everything is done by a single person. It's a relatively clean job. We don't really disturb the occupants in buildings. And here are some photos of the application. Full wrapping with glass fibers in small dimension columns to increase the axial capacity. This is an interesting project from the UK. This is confinement of columns with aramide, which is also resistant to impact. You know, those columns are sometimes hit by the drunk drivers in the UK. Hopefully we don't have some of them here. So aramide was selected as a solution here to also be impact resistant. That's one of the very first applications of FRPs in the early 90s, in the United States, involving local wrapping of large diameter circular columns to enhance ductility. there's of course no time to talk about modeling and all the details of the design calculations, but I will only say that what we need is a simple confinement model. That is, we need to somehow relate the increase in the strength of concrete or the increase in the deformation capacity of concrete to the properties of the jacket. And clearly, the thicker the jacket, the higher the number of layers in the jacket, the higher the strength and the higher the deformation capacity. If we have such a model, then we use it in our design formulas to do the dimensioning. If you look in the literature, you will literally find hundreds of these type of confinement models relating the strength or the deformation, the ultimate strain of confined concrete to the properties to the confining stress. This sigma, whatever, LUD is the design value of the ultimate confining stress exerted by the jacket in the concrete. And that confining stress can be related to the properties of the jacket and to the geometry of the cross-section. It depends on the dimensions of the cross-section, on the rounding at the corners, etc., etc. So that's the whole idea. If I want to calculate how many layers I should use, I need to have one of those confinement models and plug all my parameters. Another reason, a very important reason to do confinement in columns is when the objective is to increase ductility, to increase the deformation capacity. Typically, this deformation capacity in columns is quantified by the chord rotation of the member, by the so-called chord rotation, or by the respective ductility factor. The chord rotation ductility. The chord rotation is basically this angle here, the angle which is measured, the angle between the axis of the member prior to deformation, prior to the displacement, to the lateral displacement, to the chord of the member at failure, the ultimate value of that chord. This is what I have to increase when it comes to increasing the deformation capacity. And here is an example of how that increases easily by applying, for example, CFRP, a couple of layers of CFRP, even in columns with rectangular cross-sections in the order of 25 to 50 centimeters, as is the case in this photo. This is the response, the force versus the displacement, the lateral displacement of typical columns. It is really important to point here, to emphasize that there is practically no increase in the strength. So we don't do this jacketing, this local confinement to increase the strength of columns. We only do that to increase the ductility, to have a number of stable hysteresis loops and get a lot of deformation capacity. So strengthening is not done, is not the case. Again, calculations are relatively straightforward. We won't discuss the details. We have to relate this chord rotation, the ultimate value of this chord rotation to some properties of the jacket. There are some analytical formulas. For example, if you go by basic principles, you can relate this ultimate chord rotation to the ultimate curvature of cross-sections. This ultimate curvature depends on the ultimate strain in the concrete, which ultimate strain in the concrete depends very much on the level of confinement. And by doing that, we can do the design. Alternatively, we can use empirical formulas, simplified formulas, highly empirical, relating the geometry of the cross-section, the amount of internal reinforcement, strength of concrete, the shear span, etc., as well as the properties of the jacket to the ultimate chord rotation. This is a copy of the formula from Annex 3 of Eurocode 8. The third reason for confining columns is to prevent failures at lap splices. Again, jacketing here is local and it transforms brittle, catastrophic failures without ductility to very nice ductile ones by preventing slippage of rebars in splice areas. The mechanism is very simple. By confining those areas down here, we mainly increase the friction. We can think of a friction model, so we increase the friction here, hence we increase the shear strength of the concrete. Hence we prevent this slippage. And the delay or the prevention of buckling of the rebars is another application, is the last application related to confinement in reinforced concrete. To make a long story short, I will try to summarize this design procedure for columns. First of all, we have to make sure that the objective of our intervention, of our retrofitting, is not stiffening. We cannot make columns stiffer by using composites. So if that is not the case, then we have to design the jacket for the target value of the shear resistance. So we do the shear strengthening first, so that we satisfy the capacity design requirements. So that is, flexural strengthening comes first. And then we design for the target deformation capacity, for example, the chord rotation or the chord rotation ductility factor. And then we check the thickness of the jacket in this step for the case of rebar buckling or for the case of lap splice failures. I think I have, yeah, here is an example of this approach. Let's say, for instance, that our calculations result in 4 layers for the deformation capacity. If I need to reach a certain level of the deformation capacity, I need 4 layers. I need 2 layers to prevent lap splice failures, 3 to prevent buckling of the rebars, and 2 to eliminate shear. Then I wrap the column from top to bottom with 2 layers, and then I add another 2 at the end, so that I have 4, and that will cover all the cases. Again, I don't provide flexural strengthening. I don't solve any problems related to P delta effects, to stiffening, etc. Okay, maybe quickly we can take a look at a case study. That's a building that was retrofitted about 10 years ago in Crete. That's a beautiful island in Greece. If you have not been there, you should go. In the south part, I'm sure you know it. The objective of the intervention there was to do the job, to complete the job in about a month. That was a private hospital in the city of Chania in Crete, which was retrofitted with about 800 square meters of carbon fibers. Of course, an analysis of the structure has to be done first, a nonlinear analysis to get the response prior to retrofitting. These are capacity curves, base shear versus top story displacement. Capacity curves prior to retrofitting, shown by black, and after retrofitting, shown by red. Again, there is no stiffening in the building. There is the only result of this intervention is that the ductility deformation capacity increases considerably, extending well beyond the target that is shown by the green line. This was done by wrapping columns, by shear strengthening in the columns, by shear strengthening in the beams, shear strengthening in the joints, and of course by increasing the ductility in columns through local jacketing. Some of the cantilevers had to be strengthened in flexure as well. Well, I'll skip all the drawings and only say a few words about another interesting application in Cyprus. The idea here was to strengthen as well as, to increase the ductility as well as to increase the stiffness in a relatively flexible building with the plan view that you see in this slide. There was heavy local damage in various structural members in this structure. The retrofitting scheme was a mixed one. that involved repair of the local damage, jacketing, reinforced concrete jacketing, shotcreting in selected columns and shear walls, and as well as the application of CFRP or GFRP to increase the shear capacity of certain columns. As opposed to the capacity curve that we saw in the previous case study, here we have a slight, well, we have a non-negligible increase in the stiffness of the structure through this mixed strengthening scheme. There is an increase in the strength as well as extra ductility, extra deformation capacity. A few photos. This is the traditional method of shotcreting and reinforced concrete jacketing combined with FRPs used to do shear strengthening of beams or columns. Well, let's talk a little bit about masonry. It all started with concrete, something like 30 years ago, maybe more. And then people thought that FRPs would be a good possibility for unreinforced masonry structures, subjected mainly to seismic loading. Why? Because those structures are made of structural members which have a behavior very similar to the behavior of plain concrete. We can idealize a typical masonry structure, such as the building shown here, in many different structural members, like shear walls or column type members subjected to in-plane flexure with axial load, or we have a short beam subjected to combined shear and flexure. We have members, vertical walls subjected to out-of-plane bending, you name it. Basically, we have the normal actions which we find in concrete structures, which means that we can forget about those classical, those standard techniques for masonry, one of them being the shotcreting, the jacketing, which involves adding thickness and weight, which is not necessarily good. You see some photos of jacketing with shotcrete in masonry. There are many problems associated with that technique. The weight increases, the buildings become stiffer, the dimensions get higher, the method is labor intensive, etc. And most importantly, it is not always applicable. Due to aesthetics, because the architect will not let us do it, we cannot apply the method in many structures. And that's how it started. People thought that FRPs would be a good possibility. For example, if we have out-of-plane bending of masonry walls, we could add the fibers in a way so that they would act as tension elements. If we're talking about in-plane bending, then the fibers should be placed as far as possibly from the neutral axis to attract, to carry tension stresses, etc. One simply has to follow principles of reinforced concrete here, except for the fact that our reinforcement is not a yielding, it's not a ductile element, it's not steel, but a linear elastic element all the way to failure. When it comes to shear strengthening, in-plane shear, possibilities are diagonally placed strips or fabrics, near surface mounted, that is hidden in the bed joints, FRP rebars, surface reinforcement, fabrics covering the whole surface, etc. Well, that's not a very nice idea, but people have done it anyways. Confinement is also a possibility in masonry, confinement of domes or rectangular in-plan structures, even of columns, even of masonry columns. And I think I have a number of photographs illustrating some of those applications. Here we have in-plane shear strengthening of masonry walls. maybe a better photo. That's probably one of the very first applications in this. That was done in Switzerland in 1990, 93, 94, if I remember correctly. So you see application of CFRP strips to increase the in-plane shear capacity of masonry walls. A photo from Greece. Shear as well as flexural strengthening of a school building. Thanks to Fife for the photo. Out of plane strengthening of masonry vaults to make them stable. My colleague, where is he? Paolo. He saw some very good pictures of this type of applications. Not very nice ones. Some of them are really ugly and not that effective. But anyhow, FRPs have been applied heavily in this area. That's an interesting possibility. Again, that's one of the very early applications of FRPs. One can use transparent fabrics so that the material is not visible by naked eye. And that's also an interesting application. One can use unbonded strips or tapes as a replacement of traditional steel tendons. The advantage of this application being that the technique is reversible. The materials can be removed. Confinement using white tapes can be done to stabilize buildings to prevent out of plane bending and cracking at the intersections of walls. Confinement of columns with glass fibers is a possibility. Wrapping using strips in the form of a spiral. That's also one of the very first applications in masonry, etc., etc. I would like to skip all those very nice photos to say only a couple of words about calculations. We need to think of masonry retrofitted with FRPs as plain concrete reinforced with, I said that before, reinforced with a non-yielding material, with a reinforcing system that does not yield. So when it comes to cross-section analysis, we can adopt models that we use for reinforced concrete. We can take a look at the distribution of strains. We have the corresponding stress profiles, and then stresses or forces carried by the fibers, by the FRPs, until something in the cross-section fails. And that is either the FRP in tension or due to debonding or the masonry in the compression zone. So this is really reinforced concrete theory applied to a non-yielding reinforcing material. Likewise for in-plane flexure. That's the last part of my presentation and probably the most interesting one, I don't know. Paolo summarized very nicely some of the problems associated with epoxies used in FRP systems. Those materials are becoming expensive. They are expensive. Epoxy resins are not cheap materials. They have problems with high temperatures. The interventions with them are not always compatible, especially when it comes to historic buildings, old masonry buildings. So for a number of reasons, we thought that replacing epoxies with more user-friendly mortars, green or non-green mortars, cement-based or maybe hydraulic lime-based materials combined with fibers, including steel cords, fibers in at least a couple of different directions, that is combined with a textile type of structure. Those materials can create a composite system that does not suffer from all the disadvantages associated with epoxy resins. That's what we call a textile-reinforced mortar, as opposed to FRP, TRM. There are many names in the international literature. TRC in Germany, textile-reinforced concrete. FRCM in the States, etc., etc. So those are basically composites where the matrix is a non-polymeric one, it is an inorganic one, and the fibers are typically in the form of a textile. This system is quite effective. It is nearly as effective as FRPs. And here is the proof. If you, for example, if you confine locally a reinforced concrete column with an FRP system, with an FRP jacket, and then you do the same with a TRM jacket, with a textile-based jacket, and you compare the response of the two versus what we get in the case of a control specimen without any jacketing, you see practically the same results. There is a lot of ductility, there is very little strength degradation, plenty of ductility, no stiffness increase with both the FRP and the TRM system. So they give us pretty much the same response. And that was also tested in a, that's a touch screen. Yeah. No, sorry. I'll try to do it. That system was also tested in a nearly full-scale building in our lab, where columns were locally jacketed with TRM. With full success, no failure was observed. The building was tested up to 0.45 G after retrofitting without any failure of the jackets. Oops, sorry. It can also be used, the system can be used to do shear strengthening of beams, for example. The effectiveness here is not as high as in the case of FRPs due to slippage of the fibers if we're talking about glass or carbon rovings. It is also effective when it comes to shear strengthening of T-beams, not only rectangular cross-sections, but also T-beams. It has been used to do flexural strengthening of two-way slabs, slabs in two directions. It's an ideal system for this case because you have fibers, you have the rovings in two directions, so you can use them in both directions. But it's, according to my view, probably the most promising solution when it comes to masonry, because the mortar, the matrix, is more compatible with the substrate. The method is more reversible in comparison to FRPs. There is no epoxy, there are no organic, there are no polymers involved, and it is cheaper. It is and also quite friendly to the applicators, to the labor, to people using it. A few examples of why it works well in comparison to FRP. If you take, for instance, a masonry wall subjected to in-plane loading combined with axial force without any retrofitting, the response would have been what you see by the red line here at the bottom. If you look at load versus displacement, the response is what you get by the red line. If you do strengthening with FRP, let's say with a layer of a textile bonded using an epoxy resin, that's what you would get. If you use the TRM system, that is the same textile bonded with a mortar, with a cement-based mortar, you get a response that is very, very similar. And sometimes the ductility is even higher, as you see here. This is an in-plane flexure of a typical wall-type element, masonry wall-type element, without any axial load. Again, red is what corresponds to the non-retrofitted wall. That's what we get if we use FRP, and that's what we get if we use the TRM. So it is the effectiveness of the two systems is very similar, and the ductility in general of the TRM system is even higher. The last application of those textile-based materials was in the field of infills. We think that infills can be retrofitted. They can be retrofitted by TRMs so that they would work together with surrounding frames, reinforced concrete frames, to make reinforced concrete structures not only more ductile but also stronger and stiffer. The concept is illustrated here. The TRM is applied on the surface, one or both sides of the walls, and then, if needed, it is anchored through the thickness of the reinforced concrete elements. That was tested in the lab in nearly in a 2/3 scale, I would say, 3-story frame. With red, you see the response of the frame without this strengthening solution, and with black, you see the response of an identical frame retrofitted with the TRM system. The damage was reduced substantially. The strength was increased by more than 50%, and the deformation capacity by about the same amount. I think there is a video here illustrating the difference in the damage. You see how much damage you get in the infill if there is no jacketing with the TRM system, and how this damage is limited. There is very, very little cracking in the matrix in the case of the retrofitted infill. I will not talk about modeling. I will jump to my conclusions. The first conclusion is that the FRP strengthening method is easy to apply, fast and quite effective. There are some very basic principles which we have to respect. Loads are only carried by the fibers. Stresses, forces are only carried by the fibers. The material is not isotropic. We should not design having steel in our mind. There we have to remember this fact. The material goes linear elastic all the way to failure. There is no yielding. However, there is a lot of ductility, as we saw before, because the material has a very large deformation capacity. We can use FRPs to do flexural strengthening, typically of beams, slabs, and columns, to do shear strengthening of beams, columns, shear walls, joints, and confinement for ductility, for strength, etc., of columns. Last but not least, TRMs, those textile-based composites, where fibers, metallic or non-metallic, are combined with inorganic matrices. That's an interesting concept, and this is something that we will see more and more in practice in the years to come. Thank you very much for your attention.